Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to talk a little bit more about how to evaluate definite integrals. In our last lesson, we were introduced to the fundamental theorem of calculus, part 1, and we talked both about indefinite integrals, which is just where you take the antiderivative and get a function, and then we also dived into definite integrals, which will give you the area between the function and the x-axis. So we're going to focus on the definite integrals part today, but at the same time, to evaluate a definite integral, you need to know, how to take an antiderivative. So we'll be covering both bases as well. We're going to start by looking at, there's 5 examples. And based on those 5 examples, we're going to try to come up with 4 different conclusions. So all 5 examples are using the same function. They're using the function f of x is equal to negative 2x plus 3. But they're asking you to evaluate the definite integral using different limits of integration. So you'll see on the first one, right, the limits of integration are negative 2 to 1, and the second one, 2 to 5, etc. So I'm just going to walk you through the first one, and then I'll put up answers for the other ones, but we're not going to take time to go through the process for every single one of these. I'm also going to show you how to do these by hand as well as with a calculator. So with the first one, remember the fundamental theorem of calculus says if the function is continuous over the closed interval a to b, and I want to evaluate this definite integral, well, this is going to be equal to the antiderivative of f, so capital F, evaluated at b, which that's essentially what 1 is here in this example. So f of 1 minus f of negative 2. So I've got to find the antiderivative, and I've got to evaluate it at those 2 limits of integration. Well, this one's pretty straightforward. The antiderivative, and again, that's just a symbol right here. This is just a symbol for taking the antiderivative. So the antiderivative of negative 2x plus 3 dx, that is going to be equal to negative x squared plus 3x. Plus c, right, if we're taking just the antiderivative. But when we actually use this in the fundamental theorem of calculus, we don't have to worry about that c, right? We can just take this part right here. And that's because the c simplify when you subtract f of 1 minus f of 2. So here we are. This is going to be equal to negative 1 squared plus 3 times 1 minus negative of negative 2 squared plus 3 times negative 2. So there's a bunch of negative signs in there. Make sure we keep track of those. This is going to give me negative 1 plus 3. This is going to give me negative 4 minus 6. So I get 2 minus negative 10. That's like 2 plus 10. So I get 12. And if we think about, does that make sense in terms of this area under the curve? Well, we're going from negative 2 to positive 1. So we're looking at this area right here. And it would certainly make sense, right? That area is all positive. And it certainly makes sense that could be 12. If you want to go through and check by, breaking it into different geometric shapes and adding those areas together, you are certainly free to do that. Now, that being said, this would probably, on the AP exam, this would definitely be a non-calculator question because it's easy to find the antiderivative and it's easy to substitute in and evaluate. However, sometimes you will be able to use a calculator. And just like we were able to use a calculator to evaluate derivatives, we can also use the calculator to evaluate antiderivatives at a specific x value. Or in this case, we can actually just evaluate the entire definite integral using our calculator. So calculator will not allow us to evaluate an indefinite integral. So what it will not be able to do is help us evaluate this up here in pink. Not going to be able to do that. The calculator will not spit out the correct function. However, if you add limits of integration to it, if you put those limits of integration on there, the calculator will be able to evaluate this. So that's what I'm going to show you right now. Let's get rid of this, at least on my screen. You have it on your paper. And to use the calculator here, I don't have one available I can pull up on my screen, so I'm just going to talk you through it. This, again, would be for a TI-84 type of calculator. So you need to hit the Math button first, and then go to Option 9. And Option 9, if you're looking at it on the calculator, it just says FNINT. So that's what you're looking for. Once you click on that, it's going to bring up something that looks like this. And you just need to fill in the different parts. So you'd fill in your limits of integration. Right, you'd fill these in with -2 and 1. In here, that's where your function goes. And here is the variable that you are taking the integral with respect to. In this case, it's x. Now, a couple different ways you could enter your function, right? You could put this entire function right here into y1, and then you could just enter y1 in this little box. We've already talked about how to do that. Or you can just type in the entire function. As the function gets more complicated, it's probably better to put it in y1 before you enter it into that box. But once you fill in everything, you can use that to check your work, and you should get that this integral is equal to 12 once you fill in everything. So for the rest of the problems, a couple things I want you to do. You can do them by hand first, and then use the calculator to check. Or you can just, for these, I'll just let you use the calculator to check because we're doing the same thing, right? We're taking the same antiderivative, so there's no real need to go through that process 4 more times. So you can use the calculator to get some practice. Also, I want you to sketch what the area on the graph looks like. So just like we did it here, we shaded over the interval. I want you to shade in the other intervals as well, right? Because your limits of integration are going to be different. So look at the shaded area, see if it makes sense with the positive or negative answer you get for the actual area using your calculator, and then we will jump down and make some conclusions down below. Okay, so the first thing I'm going to do actually is just put the answers here for what the area should have been for each of these. So for this first one, or for the second one rather, we're going to get -12. For this next one, we should have gotten 0. For the next one, we should have gotten +4. And for the last one, let me scroll down here, we should have gotten -10. So those are the answers. If you got something different, you may want to go back and maybe attempt it by hand, maybe punch something wrong in the calculator, or just at least double check your work. Okay, so let's start to talk about some conclusions here. Let me make this a little bigger. Okay. And you can pause the video here and write down some things you notice based on all 5 of those examples, and then come see if your conclusions match up with the ones that I thought were the most important. And you know what? I'm actually going to put them all up here at once so I don't have to take the time writing them all down, and then we will just discuss. All right, so these are the 4 things I pulled out. In blue, the integral from a to b of f of x dx represents the area bounded between the f of x function and the x-axis. So there's a couple different ways of saying this. One way is saying it the way I wrote it, right? It's the area between the function and the x-axis. The other way that you'll hear it being said is just the area under the curve. Now, why I want to explain here why there's 2 different ways is because if you have a function above the x-axis, right, from a to b, then the area under the curve, that makes sense because it's actually under the curve. But if you have a function below the x-axis, like this, when we say the area under the curve, we are still talking about the area between the function and the x-axis, even though that area technically is above the curve if you're looking at it visually. So when we say area under the curve, we're talking about the area between the function and the x-axis, regardless of whether it's technically above or below. Number 2, if the integral number, so when we evaluate the integral, if we get a number that's greater than 0, then it must mean that the area above the x-axis was greater than the area below, right? Because the area above the x-axis is counted as positive, the area below the x-axis is counted as negative. Vice versa, if the area is less than 0, then if that number is less than 0, then the area below the x-axis was greater than the area above it. And if the area or the answer to the definite integral is 0, then the area above the x-axis must have been equal to the area below, so that those could simplify each other out. Okay, let's get some more practice evaluating these definite integrals using the fundamental theorem of calculus. Looks like there's 4 problems on this page. We're not going to go through all of them together. We're just going to go through one. And these I do want you to do by hand. So again, I want you to get practice evaluating these antiderivatives and then substituting in, etc. If you are having problems evaluating that antiderivative, well, then you can always check an answer using the calculator. But you'll just know that all 4 of these problems would probably be on a no calculator section of the AP exam. One hint I do have for you is in the bottom left, or we'll call this number 3. You may want to break up the fraction, right? You may want to rewrite that fraction as 2 different fractions before you try to take the antiderivative. I also want you to make sure that you're checking to make sure the initial condition of the fundamental theorem of calculus is met, right? There's an initial condition that says the function has to be continuous over the interval. So in number 1, we're going from 1 to 2. That function needs to be continuous over that interval. Otherwise, we cannot apply the fundamental theorem of calculus. Okay, and we would just say FTC cannot be applied, and we wouldn't actually give an answer. We'll do 1 together, and we're actually going to do number 4. So this one on the bottom right. But pause the video, take some time to work that out, and then that is the one we will go through together. Okay, so first thing we should do is check to make sure this function is continuous from 0 to pi. It is. There's no place where it's going to be undefined. There's no place where it doesn't exist. So we can apply the FTC. So this is going to be equal to the antiderivative evaluated at pi minus the antiderivative evaluated at 0. Now the first thing we need to do is figure out what that antiderivative is. So we'll just break it into pieces, right? We'll take the antiderivative of 2x, which is x squared, and the antiderivative of cosine of x, which is just sine of x. Remember, I don't need to worry about the plus c because I'm doing a definite integral rather than an indefinite integral. Now, I can't remember if we've talked about this in a previous video. I think we've just mentioned it, but we didn't focus too much on it. Before I've actually evaluated the definite integral, so once I've taken the antiderivative, but before I've substituted in, this integral sign changes to just a straight bar with 0 and pi. So let me just write this out for you. This sign means before antiderivative. Actually, there's no hyphen there. Before the antiderivative. And after you've taken the antiderivative, but before you've substituted, this is what it looks like. So if you ever see the notation with the straight vertical bar with the limits of integration, that means that the function next to it is the antiderivative. It just has not been evaluated yet. You also drop the dx once you've taken the antiderivative. So let me just speak about that real quick. Right? This on the left, this is the limit, or these are the limits of integration. And here is the variable you integrate with respect to. It would just be like if you take the derivative with respect to x, right? You're using x as the variable, but you can also take derivatives with respect to t or with what other letter is in there. Here, before you take the antiderivative, they've got to tell you what to take the antiderivative with respect to. So that's what the dx represents. Once you take the antiderivative, that dx disappears. So it would be incorrect to have a dx here, right? That would be incorrect. That's no good. So we're not going to include it. So again, just a little, I wanted to hopefully clear up any misconceptions about the notation before we take the antiderivative versus after. This one's not too bad to substitute into, right? This is going to be equal, oops. This is going to be equal to pi squared plus sine of pi minus 0 squared plus sine of 0. Remember, this would be no calculator. So I shouldn't see a decimal here when you square pi. You would just leave it in terms of pi. So I get pi squared. Sine of pi is 0. And then we have minus 0 plus 0, because 0 squared 0, sine of 0 is 0. So we are just left here with pi squared. That would be our answer. Now, after you've done these by hand, feel free to go ahead and check them in the calculator. I don't mind you checking just to get that extra practice with using the calculator. Just know that these 4 are possible to do by hand, so they would be on a no calculator section of the AP exam. And when you do this one in the calculator, you are going to get a decimal because the calculator is not going to spit out pi squared. It's going to spit out, 9 point something. But that'll also let you know. It's about 9.8696 or something as I'm looking at my calculator. Okay, we will do some practice with the other ones in class, but let's jump down here and see what's left. I think we're actually going to do this page in class as well. There is one thing I want to clarify here. Here you're given a table of values and then asked to evaluate a bunch of definite integrals. Know that it doesn't say it on here, but you can assume that the original function, the derivative, and the second derivative are continuous on the interval -3 to 5. So I know it only gives you values certain values on that interval, you can assume that all three functions are continuous on the entire interval -3 to 5, so you're able to use the FTC for all of these. And these would again be no calculator problems. Okay, we are going to wrap it up there. Hopefully you understand a bit more about how to evaluate definite integrals using the FTC. As always, enjoy the rest of your day, and we will look forward to seeing you next time.